In our previous session, we have talked about sampling. So today what we're going to do is we are going to incorporate quantization and encoding. So together sampling, quantization and encoding is going to complete the set, which is something that we call as pulse code modulation, or simply PCM. Now let us look into a pictorial view of the end-to-end communication system. For example, the one that we use for our landline networks, that is PSTN, or public switch telephone networks. So we have an analog signal which is the input, and say that this is simply m of t, and this m of t has a bandwidth of b. But note that if any signal is band limited, that means in time domain it is time unlimited. We cannot generate a band limited signal. So what we do is, for whatever signal that we get, for example a voice signal, so we pass it through a low pass filter of bandwidth b hertz, so that the signal at the output of a low pass filter is simply a band limited analog signal. And after that we have one block which we mention as a PCM block, that is pulse code modulation, and this is specifically from the transmitter side. And over here we have an analog to digital conversion. So in our previous sessions we have talked about sampling, right? And over here, by sampling, we have indicated that there is a block which is having an instantaneous sample and hold technique, and this block or this system would have a flat top pulse amplitude modulated signal at the output. So until here we have done in the previous sessions. Note that the sampling block is simply working on x-axis, that is, you have time and then you sample it as per the Nyquist criterion, right? Whereas the quantization block, what it does is it operates in the y-axis, for example on amplitude. So we would have certain levels at y-axis, and the number of levels 1 2 3 4 5 or whatever levels are there, they are mentioned by m, or simply quantization levels by l, right? So at the output of quantizer we would have a quantized PM signal. The process of analog to digital conversion is not complete here. The last step in that is that you would need an encoder to transmit this PAM signal into a specific signaling technique which would have some kind of binary bits, for example ones and zeros, right? So at the end you would have a PCM signal. This is going to be sent over a channel, for example the coaxial cable in offices or in residential places, right? So as the distance of the coaxial cable increases, there is going to be an attenuation in ones and zeros. So we have placed regenerative repeaters after a certain distance. So the regenerative repeaters are used to fix the bits so that they avoid non-recognition. So after that, this whole block is our channel, and finally we would have a receiver, that is a regenerative circuit, and we would try to get the PCM that was sent at the receiver. After that we would have, for this encoder we would have a decoder, and then we would have a quantized PM, and finally a low pass reconstruction filter. Previously I have talked about H1, in fact H0, H1 and H infinity impulse response, that is zero order, first order and infinity order hold, and eventually you're going to get the analog signal output. So with pulse code modulation, what we understand is that pulse code modulation is a method of converting an analog signal into a digital signal, that is A to D conversion. So analog signal can be converted into digital by sampling and quantization. The amplitude of analog, continuous or discrete signal can take any value over a continuous range. By this what we mean is that we have an analog voice signal, for example, and it can take infinite values in the amplitude. So over here we have time, and this is our amplitude, let's call it A. So it can take infinite values. Sampling circuit, again what we have done is we just sample it, but again the samples can take infinite values in the amplitude. So we could have infinite values over here. Note that sampling circuit is a reversible process. That is, you can go from here to here and you can come back with the help of reconstruction filters, provided that we have used the Nyquist criterion. So next is that digital signal amplitude can take on only finite values on y-axis. So that is, you're going to use a quantizer block, and on the y-axis also now we're going to get certain levels, and in this signal PM signal can only take those certain levels. So now we have on x-axis sampling and on y-axis quantization. So note that quantization is a non-reversible process. So this is a non-reversible process, whereas the sampling is a reversible process. Let us look further into quantization and pulse code modulation. So what quantization block is, that you would have a simple signal x of nts, that is a sampled version, and you will pass it through a quantizer, and at the output you would have a value which is quantized, that is xqnts, that is quantized output value. So in this figure, on x-axis we have an input and on y-axis we have an output, that is in terms of voltage. So you can observe that on x-axis we have a linear pattern, that is you can have an amplitude from minus 8 volt to 8 volt, and it can take infinite values, right? So between, for example, 6 and 8, because it's continuous, we could have infinite values, right? But at the same time, on y-axis, which is the output, so on the y-axis, which is output voltage, we can observe that it is only considering specific values, for example, minus 7, minus 5, minus 3, minus 1, 1, 3, 5, 7, right? So it is only taking those values, right? And in between it is discontinuous over here. So this means that the quantizer block is having only specific values. To understand further, let us look into the operation of this quantizer. And for that, in this figure, the dotted line is indicating that this is our analog signal, which is observed over here, right? So as a first step, we do sampling, and that sampling is indicated by dashed line, and this is over here. So at each point it is going to pick a sample and hold it, and then it is going to pick a sample, hold it, and so on. So the pulse amplitude modulation is indicated by this dash dot line, right? And finally you have quantized value, that is quantized PAM. So there is an approximation from PAM signal to quantized PM signal, and let us look into some of the examples. For example, over here, this is our PAM signal, but it has been approximated to over here. So this is our quantized signal. So this means that the input was having a value, say somewhere over here, right? So the output became 3, whereas the input was something like 3.9, right? So the input voltage was 3.9, but the quantized output was simply 3. So this is indicated over here. Again, this is our PAM signal, and we approximate it to this line, right? So this is the role of quantizer. So to note that in quantization, it is very similar to our rounding of numbers example. If we can take the analogy of rounding of numbers, for example, if we have 1.7, we approximate it to 2. At the same time we have 1.9, so again we approximate it to 2. So this means that we can do this approximation, but at the same time we cannot recover back our original signal. We have lost the signal. If it was 1.9, so we got 2, but also this 2 is representing 1.7. So once we have done the approximation, there is no turning back. So this means that we are going to have a quantization error no matter what. So in order to avoid that, what we can do is we can simply increase the levels. So presently we have now 8 levels, right? So if we have L equal to 16, so this would mean that now we would have between 8 and 6 two levels of approximation rather than one level. So if this is our line, so in this line we have separated it into sections, and we have made a centroid in this line. So if the input is anywhere in between this, so it is going to be approximated to this centroid, right? But at the same time, if you want to decrease the quantization error, so what you can do is you can make more partitions, for example, and the centroids would be in between them. So the number of levels would increase, and hence the approximation range would decrease, and hence the quantization noise would eventually decrease. So let's move on. This figure B is indicating the quantization error, that is difference between analog signal and quantized PM signal. So you can observe that it is quite evident that we are going to have certain errors, and as mentioned, this is irreversible. So once you have made the approximation, there is no turning back. So you are going to have some errors and that you cannot avoid, but you can decrease this quantization error by increasing the number of levels. Note that we have done sampling quantization, but still the encoding is left. So what we do is for each of these levels we assign certain bits. For example, this is -7, this is -5, and so on. And for -7 we assign a bit. Say this is 000, and for -5 this is simply 001, and so on, right? So this is represented over here. So we have done a digit, this is our level, and we have a binary equivalent, that is 0000001 until 111. And what we're going to do is we're going to assign certain values to this binary equivalent, that is 000 can be represented as, if this is 0 volt, this is -1 volt, so we can have -1 volt for all these zeros. So any 0 bit is going to be identified by a -1 volt, whereas any 1 bit is going to be identified by +1. So this schema is basically a signaling schema. So there are a number of schemes which I would deliberate upon in the forthcoming sessions. That is, these are line codes, right? So for instance, so as an example, let us say that this quantization level is simply 7, right? And this is our value over here, 7. And it is also represented over here, that is 111. So what we can do is, when we are transmitting, we will take this block and put it over here, that is +1 volt, 0, and -1 volt. For +1 we would have 1, 1, and 1, right? And similarly over here, this is 110, so this is going to be 6, right? So the next is 6 over here, and this is 6. So this means that we would have for here 1, 1, and 0, and so on. So based on this lookup table, we can generate the PCM code. And once we have generated the PCM code, so the analog to digital conversion is complete. A very important point to note herein is that over here the quantization levels are 8, starting from 0 to 7. So these quantization levels, as previously mentioned, are identified by the symbol L, and this is equivalent to 2 power n, where n is the number of bits. So depending on the number of bits n, we would have quantization levels L, right? So presently, since there are 8 quantization levels, so this means that the number of bits are 3, 2 power 3 is 8. So this is the reason that you are having 3-bit binary equivalent, that is 0000001 and terminating at 111. So a 4-bit quantizer, the number of levels would be 16, and you would have another bit which will be identifying the 4 bits, the value of the 4 bits. So this is a very important relationship in quantization. So let us look further into quantization and PCM. So a sample value is approximated by two types of quantizations. The first one is a mid thread, that is, so in the mid value over here, you're not giving it a rise. So it is just going to continue, and after that it is getting a rise. So this is something which we call as mid thread. And then we also have mid rise, which is in the mid value at 0 we're giving it a rise, right? So the quantized samples are coded and transmitted as binary pulses, as expressed over here. So +1 -1 +1 -1 over here. At the receiver side, some pulses will be detected incorrectly, and there are two reasons for that. The first one is the quantization error, which has been induced because of approximation in the value of amplitudes, and other one is pulse detection error. The pulse detection error is simply that you have sent 1, that is bit 1, which is representing +1 volt, but the receiver uh, estimated it to be a 0 bit, that is -1 volt. This is because of the attenuation of the signal over the channel. So in almost all practical schemes, the pulse detection error is very small as compared to the quantization error, and the quantization error cannot be ignored, right? So by this, what we mean is we have a transmitter and we have a receiver. So say the transmitter is sending a message and receiver is estimating that message, right? So there can be a feedback mechanism in which the receiver would acknowledge whether it has received the message correctly or not. So if the received message signal is not correctly determined, then the receiver can identify the transmitter and the transmitter can send again. In the meanwhile, what transmitter can do is it can also send the signal. For example, if it wanted to send 1 1, so it can repeat that code and it can send 1 1 1 1, right? So the transmitter has induced a redundancy of 2 bits. This is a waste of resource in terms of time or frequency. So but anyways, there are ways in which this pulse detection error can be corrected, but at the same time quantization error cannot be ignored. So next we analyze the quantization error. So this figure is simply identifying the quantization aspect, that is on x-axis you have the input signal and on the y-axis you have the output signal. So for example, at this point the straight line is identifying the message signal and the staircase is identifying the quantizer behavior. So at this point the error is 0 because both of these lines, the staircase and the straight line, are intersecting. So this is identified by this point over here, this point, right? So over here the error is 0, but as the value of input increases, the approximation increases until you reach this point, right? Then it will again become 0 because it's intersecting, and at these intersection points the error is 0. At other points the error would be increasing. So this error is basically identified by the step size. So let us further look into some of the assumptions. So for quantization, we limit the amplitude of m of t to a range minus mp to mp. This is just for simplicity, that if we have a signal say m of t. So we are assuming that the peak value is simply mp and the negative peak value is minus mp. Next, this amplitude is uniformly distributed in L subintervals, and each interval is delta V 2 mp by L. So this means that the peak to peak value is mp minus mp. So this is going to give us 2 mp. But at the same time, the total number of intervals, that is one starting from here 1 2 3 4 5 6 7 8 and onwards. So these are the quantization levels L, right? So they are identified by this L. So we have total uh, step size which is equal to 2 mp by L. So what this means is, so by this what we mean is that from this to this point the value is simply delta V. Since sample value is approximated by the midpoint of the subinterval in which the sample falls, so this means that the maximum quantization error is, so this means that this whole thing is delta V, and in the midpoint there is no error. So from this point to this interval over here, so this is simply delta V by 2, this one. And simply similarly over here this is minus delta V by 2. So we have delta V by 2 to minus delta V by 2. So this is our error Q. So our error Q is from delta V by 2 to minus delta V by 2, that is midpoint to the left and to the right. So the error is simply plus minus delta V by 2. And the mean square error, the mean square error is simply the power of this error signal, and for that we can identify it as q square, and this is something that we need to find. So this q square is simply minus delta v by 2 to delta v by 2 minus delta v to delta v by 2, because the error is in this range, so that's why the integration limits are like this. And then the instantaneous value of this q, which is simply q square. And furthermore, the pdf of this q, dq. So this is going to give us the mean square quantization error. Now we know most of these things apart from the pdf of q. And what is the pdf of q? So considering that they are uniformly divided, so this means that the pdf of q is of uniform distribution, and its value is starting from minus delta v by 2 to delta v by 2. And as per the properties of uniform distribution, so the amplitude is simply 1 over delta v, so that the overall area becomes 1, and this is our pdf of q, right? So we can take this value for this interval, and we can get rid of this. So this means that 1 over delta v, which is coming from here for this integration, minus delta v by 2 to delta v by 2 q square dq, and this is simply 1 over delta v q cube by 3 delta v by 2 minus delta v by 2, and this is, so if you put the limits, you are simply going to get delta v square by 12. But we have mentioned that this delta v is 2 mp by L, 2 times the peak value of message signal by the quantization levels L. So we induce this delta v value over here, and hence we would have 2 mp whole square by 12 L square, and simply this would be mp square by 3L square. So this is the mean square quantization error. of the quantizer. So this means that if the peak value of the message signal increases, that is our message signal is originally was this, which was having this peak. But if for some reason this increases, so if this increases, this means that the quantization error, that is the mean square quantization error, will increase. At the same time, if we increase the number of levels, that is, we induce a smaller staircase, right? The step size becomes small. So this would mean that the value of L, that is the quantization level, increases. So if L increases, the quantization decreases, that is the quantization error decreases. And if the peak value of the message signal increases, the quantization increases.